again. It is my pleasure to introduce Vesna Stojanoska, who will tell us all about Galois extensions in motivic homotopy theory.
Thank you, Maria, and thanks to the organizers for inviting me to speak here. It's my pleasure, and it's my particular pleasure to be here for the whole program. So thanks for the organizers of the long program for putting it together so that we can all come here and do great math together. So maybe I'll finish writing my title. So Galois extensions and motivic homotopy is what I'm going to talk about. And before I forget, this is joint work with a bunch of people. So Agnes Beaudry, Jeremiah Heller, Catherine Hess, Magda Kedziorek, and Mona Merling. Great, that fit on one line. So this is the Women in Topology 2 team and Jeremiah. So
how did you manage to do that?
I do not have a joke about this, but you already laughed, so. Okay, so we all know and love Galois extensions. For a lot of people, that's why they get into math. They learn about Galois theory, and then some of us get to do some more Galois theory when we mathematically grow up, at least a little bit. I'll talk about a finite group G. And so let's remember, what's a Galois extension? So a Galois extension of fields has lots of different, or several at least, different ways of there's different ways you can say what a Galois extension is when you talk about fields. But then if you want to translate that into what it means to have a Galois extension of rings, some of those descriptions don't quite translate. But so long time ago, I guess it was Auslander and Goldman who found the right definition. So if you have commutative rings of the form, there's A to B, a map between them, we're going to call that a Galois extension if, well, we have a G acting on B, and this map is equivariant if we think about A having trivial action. And from this data, we can produce two maps, a map from A to the fixed points of G, and a map from the tensor product of B with itself over A to maps from G to B. So let's call these maps 1 and 2. And then they say phi was a Galois extension by definition if 1 and 2 are isos. And because we're doing homotopy theory, I'll write our equivalences. And so this was a good definition because shortly afterwards, so Harrison and Rosenberg showed that there's a Galois correspondence, same as there is for fields.
That's in what Hom in what sense? What do you mean by that?
Set maps.
Set maps.
Right, and then several decades later, Rogness figured out that this actually works in homotopy theory as well. So how does it work out in homotopy theory? We have map of commutative ring spectra. G is going to act on B, and then we get to stick an H on B. and the same thing works. We may want to add a plus on G, depending on how you read that. But by the same thing works, I mean that there is a Galois correspondence as usual. And what does the Galois correspondence say? Well, it says that if we have a Galois extension, we're going to have a correspondence between, so a one-to-one correspondence or a bijection between the subgroups K of G and the intermediate extensions. And so that's where we have to add some adjectives. Separable A algebras, mapping to B, and here I have to say faithfully to B, and because we're in homotopy theory, I have to always add this word faithful, because we don't know whether it follows automatically. And this forward correspondence, it's the easy one. You assign to a group K the fixed points under the K action, and then the interesting part is in going backwards. Okay, so you want to do the obvious thing where you take the automorphisms or sort of algebra endomorphisms of B over C. And the cool thing is that you can do that. Okay, because Rogness uses obstruction theory to tell us that this thing is in fact homotopy discrete. The space of commutative algebra is homotopy discrete, so this is pi naught of itself, and it's a subgroup of pi naught of the thing. So C alg over A B to B, which is B in this case. Okay, so it just somehow works out. That's the point. So this is right. So you know, I wrote something without any condition. It's because it's the same theorem that maybe Galois figured out for fields, and then Chase, Harrison, and Rosenberg for commutative rings, and then there's a sort of Grothendieck, I guess, studied these sorts of things where you don't have affine conditions, so you want to sort of look at this in families, and then Rogness studied this for spectra and its localizations, and after that there's I guess Akil Matthew studied Galois theory in a sort of general stable infinity category setting, where you have something along these lines, and I'm not sure if the statements would exactly translate to this, but Marc Hoya has also studied an infinity categorical Galois theory where the setting is that you're in infinity topos. So anyway, so there's lots of names to be put in for various different situations, and one thing that we did in the Women in Topology workshop and beyond is and another, I guess, I should have also mentioned in one of these sort of like generalizations or abstractifications is Catherine Hess and various collaborators of hers have sort of looked at slightly stricter versions of this in abstract model categorical settings. And so we tried to combine these things together with the motivation of making a Galois theory work out in a motivic setting. Okay, so I'll just write something very brief here. Is that the thing that we did? Well, one thing that we did is to look at sort of some. We have some general setup that doesn't require you to be stable or to be an infinity topos, but only gives a forward correspondence. So there's sort of pros and cons to amounts of generalities. Okay, now this general setup applies to the motivic homotopy, unstable or stable. Okay, if you were stable, you could study these sorts of things through other methods as well. Okay, but now let's concentrate on the setting that's of interest to us. So in the motivic setting, I guess we saw yesterday, Jeremiah told us that there are two notions of homotopy fixed points. Okay, so we have the usual homotopy fixed points, the simplicial. So what do we mean by homotopy fixed points, right? So one is the simplicial, where we just declare that homotopy fixed points of G are the thing you would do normally. You have this simplicial set, e.g. You can bring it to your motivic category by looking at, say, a constant pre-sheaf that it defines, and that's a notion of homotopy fixed points. But that doesn't have the sort of desired universal properties you might want to have, and so then you see that there's a motivic homotopy fixed points. So I guess this is the notation we're sticking with. You write a blackboard bold H. Okay, G. And the point is that these two things give you two different notions of Galois extensions that we're going to call simplicial and motivic. Okay, so this is the same sort of map A to B, A, G. You are going to want to replace that with a map to also get to here. I've decided to call it motivic because geometric fixed points. Yeah. And you can then take geometric fixed points for this guy as well, and there's going to be geometric fixed points. And then how you permute those, it's going to matter. Okay, so yeah, and right, and this map actually is going to factor one way or another. Yeah, that way. Okay. So we get two notions of homotopy fixed points, therefore two notions of Galois extensions. I'm going to elaborate a little bit on the differences between these two notions of homotopy fixed points and compare that to classical homotopy fixed points. So classically, so what does that? How do we get classical homotopy fixed points? Well, one is, well, I don't know. There's lots of things, but like, what are we looking at here? What we have and now I'm going to abuse the word classical for a second, and say this. So suppose C is some, nice infinity category or something, right? So what are G, right? What do we take homotopy fixed points of? We take homotopy fixed points of things in somewhere that have a G action. And so the functorial way to say that is you look at functors from BG to C. So BG is like the nerve of the category with one object, and G is automorphisms. Okay? And there's a trivial action functor going this way, and it has a right adjoint that you call homotopy fixed points. And so this is somehow the nicest, well, I don't know. I like this picture. But another way we might get homotopy fixed points in sort of more or less the same setting when C is spectra. We use the fact that there are sort of these genuine G spectra, and so from spectra we get to make trivial action on spectra by putting them in this genuine world, and then we can localize this category and say, well, oh, okay, well, we didn't want to take all sort of these genuine equivalences, but we wanted to take underlying equivalences. Okay? And so there's a trivial functor that way, and homotopy fixed points is its right adjoint. Okay? And what does underlying fixed points mean? Well, okay, so equivalences here are detected. So equivalences here are detected on fixed points for all the subgroups of G. So what are fixed points? Well, they're maps from G mod H for H varying. Okay, so we look at maps from our orbits in, and that tells us, well, that's just taking H fixed points. Okay. Whereas here, where we put U, underlying equivalences, well, those are detected where we don't take fixed points, so that means we get to look at G mod E, right, G. So this is equivalences that detected on HOMs from G plus, okay? All right, so that's, there's nothing you said there, or, yeah.
So this right-hand thing, the underlying,
Yeah.
the same thing as just modules over the spherical group ring, or?
Spherical group ring.
Yes.
Yes. Okay. All right. Thank you for the audience participation. Which was great. Okay. And now, when we look at the motivic world, then we'll have two things that we would be able to do. Okay, so the one thing that we start with is we go from spectra to G spectra. Now there's a base S, and the order of G is invertible in S, or the sheaf of functions on S. Okay, so we have again spectra over S and G spectra over S. We have a trivial action as usual, but now there are two things we could mean by underlying. Okay, so we could literally mean underlying equivalences. Okay, or we could.
Could I stop you?
Yes.
Because Jeremiah made a point about S to GS. not being detected by the fixed point.
Exactly. Okay. Yes, that's going to be my point. That's right. So that's going to make the difference here, right? So what are the equivalences here? Well, they're not going to be just detected on fixed points, but that's why I wrote the fixed points this way. What am I supposed to what are the orbits? What's the replacement for orbits in motivic homotopy? Well, that's smooth schemes, right? So the equivalences are detected on smooth G schemes, okay? And now, when I do take that into account, and I say, well, oh, this one was the orbit that's free. So I could say here, so these guys are equivalences here are detected on HOMs out of free G smooth scheme. Whereas here, the equivalences are going to be detected just on G plus again, right? So, okay. Same as above. Okay.
But
And yeah.
yes, it's also detected on all smooth S schemes.
That's right.
You mean on G plus cross a smooth S scheme? Is that what you mean?
Yeah. Absolutely. Okay. Almost the same. Okay. Thank you.
So it's enough to test G plus cross a smooth scheme?
In here, I'm declaring this to be that. Okay. So this is a localization of this category. And there's I guess a map where this way.
But that's not an equivalence problem, right?
No. Yeah, and so the whole point of this is that now I have this trivial action compositions, and let me take color. Green, maybe green will work, I don't know. Can you see this? The right adjoint of this one is the simplicial homotopy fixed points, and the right adjoint of the other composite is the motivic homotopy fixed points. Okay, and the reason that I'm spending the time drawing this picture for you is because the sort of the setup for doing Galois theory in an abstract setting is based on having nice adjunctions, and these are that kind of nice adjunctions. So up until the point where you get to do the sort of backward Galois correspondence, everything is fairly formal, and so just having really nice adjunctions with good symmetric monoidal properties will get you there. Okay.
Before you go on, so the map that you've labeled Trev, does that have a right adjoint?
Yeah, that's fixed points, like categorical fixed points. Yeah. Okay, so now I'll tell you about examples, because, well, we like examples. And maybe, okay, I don't know. Maybe I shouldn't be making this comment because I don't have anything meaningful to say, but I'll go ahead and do it anyway. I wrote this adjunction down, and this is the basis of what, say, Achille Matthews' theory of Galois, or sort of Galois theory in sort of very general settings is based on. So that thing is like, if we were trying to do this motivically, it would only apply to the simplicial homotopy fixed points, and we're still trying to understand what is the correct analog for the motivic homotopy fixed points. Okay. There's no Yeah, I have to erase. So maybe now is a good time for more questions. Okay. So here's a very simple example. Trivial extensions. Okay. So wherever we are, we can usually make this object and a map this way, and whatever our notion of Galois extension should be, that should be an example. And so, indeed, so if say A is a commutative ring in wherever your homotopical theory, wherever, this is a simplicial Galois extension. But if we're in the motivic situation, this is both simplicial and motivic Galois extension. And I mean, of course, I'm assuming here that A has a trivial action. Okay?
Using the label.
That's right. So this is, I mean, a better way to write this, I guess, if we're doing spec. Or G plus. Okay. Yeah. Okay. Now, stably, this is equivalent to G smash A. Okay? And what was G in the motivic setting? It was just a particular free G scheme. Okay? So here's an elaboration of this example. Proposition. Okay, so we start with a G torsor over S. So an étal G torsor. And so, for example, if S is spec of a field, then X could be spec of a Galois extension of that field. And so we take A to be a spectrum, a ring spectrum over S. And then the claim is that then A2 X plus A is motivic G Galois. Okay.
So Vesna,
Yeah.
S is then a Galois extension of schemes, right? Same.
That's right. Yeah. Yeah. Yeah, exactly. So so Galois extensions, or torsors, étal torsors in schemes are going to give us extensions this way. Okay, and just looking at it this way, at least if I were to look at this for the first time, it's not clear to me what the algebra structure would be on that right-hand side. So maybe that's something I need to tell you first. Okay, so in order to write that down, we'll write down, let's say, where that came from. Okay, so that map F produces for us some adjunctions. Okay, so we look at G. Oh, yeah, right. We look at G spectra over S and G spectra over X. There is a restriction functor, and that one has a right adjoint and a left adjoint. The fact that this F is a tau, it's going to tell us that these adjoints agree. Okay. The restriction map is the usual. It's a base change. This lower sharp map is you have, it comes from the map that say it looks at a scheme over X and just considers it as a scheme over S. Okay, so it just composes the structure map with F. But this lower star is just what it is, right? And so it's great that we're in a setting where these two guys are equal. And this is where we need to be stable. Something like this doesn't work out stably. Okay, so okay. And now what do I have? I have a map from A to, so I have a unit of this adjunction. Okay, but if I write it in the other order, okay, so what is this? I'm base changing A and then considering it as a thing over X. So this is X plus A considered over S. Okay, so that's what the map is. And these, like F upper star is monoidal, and so F lower star is lax monoidal, so this gets an algebra structure as needed. Okay, so the fact that F was an étale G-torsor, meaning a Galois extension, so gives us that X, I guess this thing is equivalent to G plus smash X, or however you want to write that. So this implies the second map in the Galois thing to be an equivalence. So that, okay. Remember that was that this guy tensored with itself over A was going to be just a bunch of copies of A. And yeah, and the second thing I need to convince you is that the motivic homotopy fixed points of this guy are A. Okay, so let's look at that. It again only depends on like the properties of these functors. But yeah. Okay, so what is that? I guess I'm doing this thing. Okay. So okay, actually, by definition, what is this? So we are looking at functions from EG plus F upper star of A. Take the fixed points, and then okay. So this guy's a right adjoint, so I get to move it here. And now F upper star is also a right adjoint, so I get to move it. So that's F lower sharp, F upper star of EG. G. Okay, and now let's look at this thing. I gave you the formula for what F lower sharp F upper star is. So that's just X plus smash EG plus. Okay, but okay. So this, what is this? This is a free G thing, and I'm smashing it with EG. What does EG do? It frees things up. Okay, so this was already free, so that's equivalent to X plus. And now these fixed points, well, they also, because X is free, I get to take orbits, and this is from x plus mod g to a. And because that I'm using again that f was a torsor, and that's just a. And maybe you can trace through these adjunctions that indeed that map is the equivalence. So there's some non-trivial facts being used here about this situation. So I should probably attribute them to somebody. And I don't know if the history of the problem, but these are in Mark Correa's six-functor formalism paper for sure. There may be precedents that I'm not exactly aware of. So apologies if I've missed somebody's name. Okay. All right. So that takes care of the trivial extensions. And it's sort of like, I don't know. Well, anyway, these trivial extensions are just somehow like a sanity check. Okay, so you want, it just makes sense that they are, that they're there. And this isomorphism, I guess, is related, right? So what have we been doing here? It's a generalization of a Wertmüller isomorphism that's going on in this picture. I don't know, generalization, analog at least. Okay. All right. So that's all about that example. But the real cool example, I think, is for K-theory. Okay. How do you draw a black bold? Bold 2. I don't know. Okay. Right. So here's a theorem. I guess this proposition as well as this proof are due to this team. Okay. So that is, okay, so we look at Hermitian K-theory. Mapping to KGL, algebraic K-theory spectrum. And it's C2 action given by Adams operations, taking the dual vector bundle. So the claim is that this is motivic Galois. Okay. The normal font version of this is that we want this thing, the same thing, to be simplicial Galois, but it's not. Have to complete here at eta. Okay. So we'll have examples of all sorts. So here is one which is motivic but not simplicial. Well, no, yeah, I don't know. And here, if the torsor is non-trivial, these are not going to be simplicial. So they're only going to be motivic. Okay, I guess we also know examples of things which are simplicial Galois, but not, at least we don't know that they're motivic Galois. Those come from Eilenberg-MacLean spectra. Okay, so, right, and of course, both of these are analogs of Rognus's observation or theorem that KO to KU, so the real K-theory spectrum to complex K-theory spectrum, is a C2 Galois extension. And now this one is really cool because, like, even, you know, let's think about ordinary homotopy theory, the usual KO to KU analog. Okay, so this is like an extremely useful statement, knowing that this is Galois, because Ku is a very simple spectrum, right? It doesn't have any torsion in its homotopy groups. It's even periodic. It's all sorts of things that you would want. And Ko is not. But that, you know, this fact that this map is Galois, it makes studying Ko easy, like much easier than you would expect from just, say, looking at its homotopy groups. The downside of this example is that there aren't that many intermediate, extensions, or at least we don't know, but there aren't that many intermediate groups between the trivial and C2, so we can't really test the Galois theory so much. Who knows? Maybe that means it's a good test case. Okay, so let's, before getting into the proof, maybe again I should list a long list of people who've worked on these problems or related problems. The fact that the simplicial homotopy fixed points of KGL are this eta completed KO, I guess that problem has a long history. So, slowly but surely, sort of stronger and stronger statements leading to this one were proved. So, I guess Hoek-Ries-Ormsby proved the version where KO had to be also 2 completed, and then the base has to be pretty restrictive, and then there were probably step-by-step sort of generalizations by that, I guess, and now I lost my list of of people to attribute this to, but Rundigs, Ostphal, and maybe somebody else, Spitzweg, thank you, worked out this equivalence over basis of virtual cohomological about 2 primary dimension, like finite, and then Drew Hurd proved the sort of more general setup, more general statement along these lines. We can also give a different proof using equivariant homotopy, sort of motivic homotopy theory. So by now this is like a well-known fact, but a lot of people have contributed to that. Okay, now, so let's catch the proof ideas. So, right, so there were 2 things to prove that, for something to be Galois extension. Okay, so one of them, so that KGL smash KGL over KO is equivalent to this thing. So wrongness catches a proof for this in the sort of classical analog, and that proof just goes through if you feed in the corresponding facts about the motivic spectra involved that Rundigs and Ostphal have proved. Okay, so that thing works out, and it's the same for both simplicial or motivic. Yeah.
No.
Something like the cofiber on eta on KO is KGL, and what happens when you compose the sort of the analogs of the complexification and the realification maps.
This has nothing to do with taking, right, you're not taking geometric fixed points.
No, yeah. Okay, so now let's see why should this thing be an equivalence. Okay, so I'm going to just state an assumption that we have a ring spectrum, like actual equivariant motivic ring spectrum Kr. Okay? Such that, so we want a real version, right? So this is a version of a TS K theory, and the following things is what we demand from this guy. Okay, so underlying spectrum with C2 action is going to be just that KGL. If we take the categorical fixed points, we're going to get KO, the Hermitian K-theory spectrum, and we demand periodicities. So we want this to be S sigma smash GM periodic. And so what is this? The S sigma is, I guess, it's the Tom, right? It's the simplicial circle with the sign action. Okay, and so it's the one-point compactification of the sign, real sign representation, and then the constant preshift that defines, and also S1 smash GM sigma smash KR equal to KR. Okay, and so what is this sigma? So this is now that we are acting on GM by inversion. Okay, so I guess right. So these periodicities appear in the Hooker-Ormsby work that I mentioned, and I guess also maybe they originate from Karoubi's work on Hermitian K-theory. So they're reasonable things to expect from KR. Okay, so given this, let me show you how you can get this to be an equivalence. Maybe now I can start using the sideboards. So we need to show that KO is that. So instead of KO, I'm going to take the fixed point. So you see how this is the kind of a homotopy limit type problem. Okay, so we're trying to see that the fixed points to the homotopy fixed points is an equivalence. Okay, so yeah.
Can you say
Absolutely.
That this exists? Is it known to exist?
Not in the literature. I am not exactly sure what the current status of this is. Do you want to comment on that?
It can be done.
I didn't hear that.
It can be done, he said. Okay.
Someone has to write it down.
That's right. Nobody wants to take up that responsibility and write it down. But I think a lot of people agree that such a thing exists. Yeah.
What's the issue then?
What was that?
What's the issue? Why don't we write it down?
I don't know. So personally, everyone has different reasons for not, I guess, not writing down things.
Do I have a reason for not writing things down?
I feel like this is not, so I can only talk for myself, and I feel like this is not my, like, I don't really get what the, I'm just going to assume this and make some computation. So I'm not the kind of person who gets into the, into that kind of business, and I feel like it's not my result. So I don't feel responsible for writing it down, and I don't know what the reasons are. Like, I
Someone's
don't
gonna
know.
write it down.
Does it represent
someone's
anything
gonna
reasonable on G scheme?
On G schemes.
On C2 schemes.
Yes.
Something- yeah.
Yeah. No, it should be so what does KO represent? So I guess it's the kind of thing that you want KO to represent, but with the equivariance on your base taken into account.
Oh, okay.
Yeah.
Like KO for rings with involution.
Exactly. Yeah. Okay. So, all right. So what do we do when we want to show that two things are equivalent? We have a map between them. We take the fiber, right? And so maybe this will make John happy. So what's the fiber? The fiber is going to be the equivariant maps from this EC2 tilde guy. And so what's EC2 tilde? We have, here we map from EC2 plus. Here we go to the sphere. That's what that guy is. EC2 tilde is the cofiber of this by definition. Okay? And there's a geometric model for this universal space EC2. It's the co-limit of the affine space in n sigma, then minus 0, 0 is the fixed point set. Okay? And so we get that this guy is co-limit of these t and sigmas, where this is the Thom construction that Mark denoted s to the n sigma. And so as is usual in these sorts of things, like what do we need to do? Like these, right? Okay. So what are the maps between these? They're iterates of the this Euler class, the inclusion of fixed points from S0 to T sigma, and T sigma is the smash product of this simplicial circle with the sign action and GM sigma. And so this, let's call this Euler class B sigma, is the product of two Euler classes, one for this guy and one for that guy. So let's call those A sigma and A GM sigma. Okay. So all we have to show is that this class B sigma, or some product of these two guys, is nilpotent in KR cohomology.
The two non-trivial fixed points.
That's right, yeah. Okay, so am I going to be able to fit this on one board? Maybe. All right, so we need to check what's going on there. So let's take some some power of this thing, B sigma to the n, and also smash with the unit in KR. So this is the ring spectrum, right? It has a unit. N sigma. And okay, so because this was a product of those classes, we can write this as a composite. So I'll take A sigma n times. And then I'll take A GM sigma n minus n minus 1 times. And then one more time. Okay. And okay, so now we're going to use these periodicities. Like the trick is going to be that neither one of these is nilpotent. Okay, so if you were doing this, yeah, maybe I should pause for a remark here. If you were doing this for the classical situation for KO to KU, you have a TSK theory KR, you look at the Euler class for the sign representations, and you relate that to multiplication by eta. Multiplication by eta is nilpotent, so you get the result that you want. Here, multiplication by eta is not nilpotent, so you don't get that. But multiplication by eta relates to one of these guys and not the other, probably this one. So you're not going to get the nilpotent thing there. But this composite here, that's going to be something nilpotent. Okay, so how do we do this? We want to say, well, right, and we only care to know that the fixed points are contractible. We don't have to worry about this being equivariantly contractible. And so we want to take a maps from here to here. That thing has trivial action. It's going to factor through the fixed points. And so now we want to take fixed points of these guys. And that's why we need the periodicities. So I don't know what the fixed points are the way it's written, but the periodicity thing is going to tell me that this thing is equivalent to KR smash GM minus N. Okay? And now this thing doesn't have an action, so if I want to take fixed points, I can commute with the smash product. But the more importantly is if I do that here, okay, so that I'm gonna get using the periodicities that this is GM minus N smash S minus N plus 1. Okay, and now I'm looking at this map. What is this map? Okay, so this map is going to give me a class in KO, and now I have to use this, minus 2n plus 1 comma minus n s naught. And maybe so here's a trick. Okay. This is I guess this thing has different names. So this is a Grothendieck bit group minus n minus 1 of the base, and I guess that's like a fit minus n plus 1 of s. And then you say, well, okay, n could vary, and is this thing 0 for some n? Okay, these guys are 4 periodic, and you go and look at Balmer's work on these guys, and you find that a lot of times that's 0. So in particular, it's so for example, if n is 2, this thing is 0 over something like z adjoin 1/2, also over various spaces, but I guess the idea of, maybe I should have said theorem in progress, whereas various iterations and various improvements could be made over time, is you know once you know it here, use base change to deduce over a general base over that, and so we get the result. If you don't believe in base change, you can pick your S so that some higher bit group is 0, and then you'll have a statement there. Okay, thank you for your patience.
So you started out saying that G is supposed to be a finite group. I mean, John works in a more, and we're gonna see works in a more
Right.
general context of stably dualizable groups. Does that
Um,
for you hold true here as well?
Yes. I so at some point, right? So there are two inputs. One is the sort of the setup where right, where you from homotopy theory, what works that way, and then another one is in motivic homotopy. You want a good setup for motivic G spectra, and what could G be, right? So then you also have the question of like algebraic groups other than constant groups and stuff like that. So I believe like there's lots to be said in much more general situations. We just haven't spent time looking at examples as much. The original Women in Topology project was concerned some very general setup where you look at like a Hopf algebra object in whatever category you're in, you know, stably dualizable type thing, and the sort of the general theory works out the same way. But the general theory only gets a forward Galois correspondence. So yeah.
When did 2 get inverted in the base?
Oh, a long time ago, I guess I said that when I talk about G schemes, I do want G to be invertible in the base. Yeah, so I assume that that's always the case. And also, I guess every time I would write KO, I would want 2 to be invertible. So yeah. Yeah.
So in this proof at the very end, which part was sort of in progress? Because I mean, it sounded like a convincing argument to me.
I guess what I need to do for myself, and I apparently haven't done this, or maybe I'm not willing to claim that on the fly, is what sorts of statements do you get to translate under base change? I mean, we're talking about this KR, right? And so we would need to know that it's a sort of it's a base change invariant or something. Like I don't know. So that when you base change it, you get the same thing. But I mean I believe it. It's just I'm not super confident about how exactly it works out.